All right, let's take a look at problem 8. So problem 8 and 9 are going to differ from the previous problems in that now we'll work with our cubic equation of state. So we've used a truncated virial equation, we used the Kessler, now we're going to use our cubic equation of state as our method to calculate Z, our compressibility. So just as a note, before we work on the problem, I just want to point out there's a new page. There's a page in the Chapter 2 module, Cubic Equation of State Example. And so this is from when this is material that actually I've posted on YouTube several years ago, where I provide some MATLAB code to calculate volumes and compressibilities using cubic equations of state, specifically van der Waals, SRK, and Peng-Robinson. And I demonstrate their use, for example, 2.11 in the text. So that video is posted on YouTube. So I'm going to use the code for SRK in this problem solution, so that will serve as an example for you. But do know that this is here, and this material was created when I originally created that code to demonstrate it. And so what I'll do is, in our solution, I will start with that code and just modify it and update it for our problem. Okay. But all right, so let's give it a try. And I just want to make one disclaimer, right? So use my MATLAB code. So, the goal of this course isn't for you to spend a lot of time writing MATLAB code to solve cubic equations of state problems. I use MATLAB to solve my cubic equations of state problems because I find it to be a whole lot easier than using Excel. Okay. With MATLAB, I can readily generate, all roots all at once and use their built-in numerical methods to solve. No need for goal-seek and iterating. The key thing I want you to remember is that the basic operation of our cubic equation of state, so if I think of my MATLAB code as a black box, is if I know temperature, pressure, and then I look up TC, PC, and omega, I plug that into my black box, and out comes Z, all right, and equivalently V, molar volume. Okay, so what I'm really solving for is Z. I can then back out V because V is just going to be ZRT over P, right? Where I know T and P. Then the key is working with my cubic equation of state in this standard mode, if you will, and this is going to be the standard mode that we'll use in problem 8 and 9, is that if I get multiple values of Z, I just need to decide which value to use, right? I need to know what phase I'm in. So when it comes to Z and V, if I get 3 real roots, if I get 3 real values out, the largest Z and V correspond to vapor, smallest correspond to liquid, middle we always throw out. All right, so if you get more than one real, and that could happen if I'm close to saturation, then I just need to know what phase I'm in to decide which root to choose, or if I'm at saturation and I choose both. Okay, so use my MATLAB code. The intention of using MATLAB is to make life easier. What I want you to take away from all this is what equation of state is, how you use it, what they could be used for, not spend an hour writing some MATLAB code and then trying to debug it. Okay. All right. So problem 8. So we have a 0.5 meter cubed tank. So V total is 0.5 meters cubed. That's going to be used to store CO2 at 20 degrees C. So let me make sure I get the temperature right this time. Use the SRK equation of state to answer the following. Determine the maximum amount in kilograms of CO2 that could be stored safely if the tank can withstand a maximum pressure of 70 bars. Then we're repeating at 60 and 50. All right, so let's kind of work out this general strategy. Okay, so we know V total is 0.5 meters cubed. Temperature is 20 degrees C. Okay. What's key here, as I said, in goes temperature, pressure, TC, PC, and omega. So it's imperative that your temperature is in absolute units. All right. So use Kelvin, right? Because ultimately you're going to calculate a reduced temperature, right? So temperature, make sure you're using absolute units. Use Kelvin. Pressure, essentially you just need to make sure that PC and P are in the same units. When it comes to using my MATLAB code, keep temperature in Kelvin and keep your pressure in bar, right? So the units of pressure, so in theory, reduce pressure, you just need to make sure you have the right units. But when working with the equation of state, it does affect some of those constants for the form that we're using. So temperature in Kelvin, pressure in bar. Okay, so this temperature of 20 degrees C, okay, I'm going to convert to, this will be 293.15 Kelvin. Remember, just add 273.15. All right, and then, when I think about A, okay, so A, we're told that my pressure is equal to 70 bars. Okay, cool. So we already have the desired unit of pressure. So in A, right, we want to solve for the mass of CO2 that could be stored, or essentially, the moles, and which we can convert to mass. So the general strategy is going to be, one, I look up TC, PC, and omega. Okay, then using my cubic equation of state code, right, I can calculate V. Okay, and if I get more than one V, right, what phase do I have? Well, in all cases, I'm at 20 degrees C. In A and B, my pressure is greater than the corresponding saturation pressure. So in both of these cases, I'm going to have a liquid. Okay, so in A and B, I have a liquid since my pressure is greater than Psat at 20 degrees C. C, I'm less than. Okay, so C, I'm going to be a vapor. Okay, so if I get more than one real root, I have to choose the appropriate. So I'll choose the smallest in this case. I'll get V. And then once I have V, I can calculate N. Because remember, V total is equal to N times V. So therefore, N will be V total, okay, which we're given, divided by V. And then finally, to get mass, okay, mass will be equal to moles times my molar weight, which is grams per mole, right? And we'll take care of the units here in a second. And then we'll repeat. Okay, so what I'm going to do is I'm going to go, and right now I have the MATLAB code open that I posted, which is based on example 211. Okay, so just to demonstrate how I'm going to go about this, is I'm going to save this as chapter 2, and I'm calling this example 9. Okay, all right, and I'm just going to clean it up. So in this problem, we're dealing with CO2, carbon dioxide. So I'm going to need to go look up critical temperature in Kelvin, critical pressure in bar, and my eccentric factor. And that can be found, right now, this is the appendix for our text. So for carbon dioxide, here we go. TC is 304.12. Critical pressure, 73.74. And eccentric factor is 0.225. Okay, and before I forget, right, I renamed this example 211, but do note that we're going to use this SRK code, this function, so it also needs to be here, right, in the same directory. All right, so there are temperature and pressure of interest. So my temperature is 293.15. And my pressure is 70 bar. Okay, so it's in bar. And so let me make a note. This is for problem 1, or call it part A. Okay, and so then, okay, I'm going to delete a bunch of this code because we only need to get, all we need is molar volume, right? So all we need is molar volume using SRK. So I'll delete van der Waals and Peng Robinson. And then I have the code set up so it'll return molar volume, compressibility, and ideal gas molar volume. But I just want V, so I'm just going to delete the others. Okay. And so I'll call this code V SRK. I pass to it temperature, pressure, eccentric factor, critical temperature, and critical pressure. Okay. And just to demonstrate this, if I click run, okay, I get my volume, right? 65.0961. Okay. As for units, okay, so the units should be centimeters cubed per mole. Yeah, this is going to be in units of centimeters cubed per mole. Okay, so let's take note of what we have. So I get a volume, and my volume is 65.0961, and that's centimeters cubed per mole. Now my total volume is in meters cubed. So either I'm going to need to convert my total volume from meters cubed to centimeters cubed, or convert this. Okay, doesn't really matter. Okay, what I might do is let me convert V total. And so remember, in terms of the conversion factor, so let me just write it down here. V total is 0.5 meters cubed. And then to convert, we have that. So we know we have 100 centimeters per 1 meter. So I have 100 centimeters cubed per 1 meter cubed. Okay, or to make it a little more compact, I have 100 centimeters cubed per 1 cubic meter. Okay, and so that'll allow me to convert V total to centimeters cubed. Okay, so let's get this. So V total in centimeters cubed. So V total is 0.5 times, this could be 100 cubed. Okay, so now to get, and so just leave it like that since we have it in MATLAB. So then V totals in centimeters cubed, V is in centimeters cubed per mole. So I can solve for N, which will give me mass in moles, or volume in, so this is in centimeters cubed, this is centimeters cubed per mole, so I'll get N in moles. So solving for N in moles. When it comes to dealing with V, we only have one, so that works out. So N will be equal to V total divided by, okay, and so I'm going to put that in before I forget, centimeters cubed per mole. So my tablet gets touchy sometimes, it's sitting in front of me. So that'd be V total divided by, up there I call this V SRK. Okay, so that gets me the number of moles. Then once I have the number of moles, I multiply by molecular weight. Okay, molecular weight of carbon dioxide should be in the same table. Carbon dioxide molecular weight is 44.010. So molecular weight, 44.010. Okay, so this would be in grams per mole. And the problem, do we want kilograms? You want to know the total amount in kilograms. Okay. So if this is the molecular weight in grams per mole, 1,000 grams equals 1 kilogram. So if I want the molecular weight in kilograms per mole, that's the molecular weight in grams per mole divided by 1,000. All right, so then to get mass, I just need moles times molecular weight. Okay, so now Moles is moles. This is units of kilograms per mole. So mass in kilograms will be my moles times my molecular weight in kilograms per mole. And that is 338.0384. So 338. 338.0384 kilograms. 338.0384. I forgot a zero. Okay. Cool. So that's A. B. Okay, now that's a liquid. So now let's look at B. So B, the only difference is my pressure is now 60 bar. All right, and so what I expect, okay, is when I look at A and B, right, both are liquid since my pressure is greater than Psat. So these are going to correspond, or this is going to correspond to a compressed liquid. So I have a liquid, right? I'm changing the pressure, but temperature is constant. So I would assume that the volume wouldn't change much, right? So I would expect that the amount that that tank can hold is going to be pretty similar, right? It might decrease a little bit because I'm decreasing the pressure, but right, I would assume that it's going to be pretty similar. So all I need to do, right, is for part B, I just need to update the pressure and recompute part of this. Right? So now for part B, my pressure is 60. Calculate volume the same. Total volume's already been defined, so that's good. Calculate N. Already have my molecular weight, so I can calculate mass. Okay, so let's give it a try. The one thing we're just going to have to see is if we have more than one real root. Okay, so what we see in this case is they actually have 3 roots for V. Okay, and so let me change this to an element-wise operator, make sure it works. Okay, and so we get 3 V's. Okay, largest being 200, lowest being 68. Now, if I go back, okay, we said we have a liquid. Okay, so if I have 3 V's, okay, I'm going to want to choose the smallest V. Okay, and notice my smallest V is 68.8325, which doesn't deviate too much from the 65.0961 we had in A. Okay, so I'm going to use VSRK, but if I want, I can use just that final root. So you can use 3, or I'll use the keyword end just to print the last one. So the mass that we can hold is 319.6889 kilograms. So my mass for B, okay, again, it's the exact same problem, just changing P. So we have 319.6889 kilograms. Okay, now C is going to be different because C, our pressure is 50 bars. Okay, and as we said, okay, at 50 bars, we now have a vapor. Okay, because my pressure is less than Psat at the same T. So in the first two, I have a liquid, but now I have a vapor. All right, and notice in A, I just had 1 real root. Okay, B, I'm getting closer to saturation, so I had 3. All right, so even though I'm a liquid, right, I got 3 real roots because I'm getting pretty close to that saturation curve. So in C, if we get 3 real roots this time, we'll need to make sure we choose the largest volume because we have a vapor. Okay. And what should happen is since we have a vapor, we're going to be storing much less of our CO2 in that tank. All right, so by compressing CO2, by storing CO2 as a liquid, we can store a lot more of it. Right, it's kind of like my propane tank on my grill. Right, You don't want to know about that. Okay, so I have a pressure of 50 bars, and in this case, it's going to be a vapor. So all I'm going to do here is I'm going to copy, okay, what I had for part B. And now this is going to be part C. And we have 50 bars. Okay, and let me comment out these last two lines for now, because let's see if we get more than one V first before we go picking one. Okay, yeah, we get more than one V. So now the difference is now I have a vapor. Okay, so before we were choosing the smallest V, which corresponds to liquid. Now we're going to need the largest V, which corresponds to vapor. Okay, so when we calculate N, rather than use the smallest V, right, the last one, we're going to use the first one, which is the largest. Okay, so we end up getting a mass now of 69.1772. So the mass that I can store when CO2 is a vapor is 69.1772, and that's kilograms. Okay, so now the mass, all right, that I can store is substantially less because here I'm storing it as a vapor, or in the previous two parts I was storing it as a liquid. All right, and so the mass doesn't change much, all right, but here now you get this abrupt change when now it's being stored as a vapor. Okay, well, hopefully that helps. Okay, again, use the MATLAB code, right? The goal is for you to understand how to work with cubic equation state, what they're capable of, what goes in, what comes out. So more the concepts than writing the actual MATLAB code. Okay. Remember, even your exam will be open book, so if you had to solve a problem with your cubic equation state, you're more than welcome to use my MATLAB code. Okay.